Look around for a moment. Every second of your life moves in one direction, forward. You remember yesterday, but tomorrow remains a mystery. A broken glass never reassembles, smoke never gathers back into the flame, and stars never grow younger again. But here's the strange part. The fundamental laws of physics don't strongly prefer the future over the past. At the smallest scales, the equations of nature work almost the same whether time runs forward or backward. So why does the universe seem to have a direction at all? Why does time flow like a river instead of standing still? In this video, we're going to travel from atoms to planets, from galaxies to the birth of the universe itself, to uncover one of the deepest mysteries in physics, the arrow of time. Because somewhere in the history of the cosmos, something set time in motion. And once you see where that direction may have come from, the universe and your place inside it may never look the same again. Every moment of human life seems to move in a single, unmistakable direction. Yesterday fades into memory, today unfolds before us, and tomorrow remains unseen. No one has ever watched time reverse itself. No one has ever stepped back into a moment already lived. Yet the deeper question lingers quietly behind every passing second. Think about the simplest events in daily life. A glass falls from a table and shatters across the floor, but the broken pieces never leap upward, reforming the glass in midair. Something about the universe seems to prefer forward motion. Memories offer another curious clue. People remember birthdays that already happened, conversations already spoken, and journeys already taken. But no one remembers tomorrow's weather or next year's discoveries. It's as if the past leaves footprints, while the future remains unwritten. Across nature, the same pattern quietly appears. Day becomes night, night becomes morning, and seasons march forward, one after another. Spring blossoms give way to summer heat, then autumn leaves, then winter cold. Time never seems to circle back to where it started. So the mystery emerges. Why does time appear to have a direction at all? Why does the universe allow events to unfold from past to future but never the other way around? Somewhere within the laws of nature, something must be guiding this cosmic flow. And to begin unraveling that secret, we first need to observe how this strange direction appears everywhere around us. If someone quietly observes the world around them, a pattern begins to appear almost everywhere. Events don't unfold randomly in time. They follow a clear direction. Moments seem to flow like a river, always moving downstream. And once something has happened, the universe rarely lets it happen in reverse. Imagine placing an ice cube on a warm table. Slowly it begins to soften, shrink, and melt into a small puddle of water. But no one has ever seen that puddle suddenly gather itself, rise upward, and freeze back into a perfect cube. Nature allows one direction of change far more easily than the other. The same thing happens when smoke drifts through the air. At first, it leaves a flame as a tight, swirling column, but soon the smoke spreads out, dissolving into the surrounding atmosphere. It never magically pulls itself back together into a neat stream. Even on the largest scales, the pattern holds true. Stars are born inside dense clouds of gas, shine for millions or billions of years, and eventually grow old. Some collapse, some explode, some fade into quiet remnants drifting through space. But no ancient stellar corpse has ever been seen reversing its life and becoming young again. So whether it's melting ice, spreading smoke, or aging stars, the universe shows a strong preference for forward unfolding. Processes begin, evolve, and move toward new states that never quite rewind. This directional behavior appears so consistently that it feels built into reality itself. But when scientists look deeper, down to the smallest building blocks of nature, the story suddenly becomes far more puzzling. Now the journey moves deeper, shrinking down beyond everyday objects, past grains of sand and droplets of water, into the hidden world of atoms and particles. At this microscopic scale, reality behaves in ways that can feel almost counterintuitive. The laws that govern these tiny building blocks are surprisingly indifferent to the direction of time. In fact, many of them work perfectly well, whether time moves forward or backward. Imagine filming two billiard balls colliding on a smooth table. If the video were played in reverse, the motion would still look perfectly normal. The balls approach, collide, and roll apart. Nothing about the movement reveals whether time is moving forward or backward. At the level of simple physical interactions, the universe often doesn't seem to care. Atoms behave in much the same way. Particles bounce, scatter, and interact through fundamental forces that remain mathematically symmetrical in time. The equations describing their motion don't strongly favor past over future. To the raw laws of physics, forward and backward can look almost identical. But something curious happens when many particles gather together. Instead of a handful of billiard balls, imagine trillions upon trillions of atoms interacting at once. Suddenly, order begins to dissolve into complexity. Patterns spread outward, energy disperses, and systems begin to behave irreversibly. It's a bit like dropping a drop of ink into a glass of water. At first, the ink forms delicate swirling patterns. Then, it slowly spreads until the entire glass turns faintly blue. The particles themselves follow simple rules, yet the overall behavior suddenly reveals a direction in time. So while the microscopic laws may allow symmetry, large collections of particles create something new. Out of countless tiny interactions emerges a sense of irreversible change. And once systems grow larger, planets, landscapes, entire worlds, this forward march becomes even more dramatic. To see that, the journey now expands outward to the scale of planets. Now the perspective expands outward again, from invisible atoms to entire worlds drifting through space. Planets are not static objects frozen in time. They are dynamic systems, constantly changing, reshaping, and evolving across vast stretches of cosmic history. And every one of those changes unfolds in a clear forward direction. Take the surface of a planet like Earth. Mountains rise slowly as tectonic plates push against each other. Wind and rain gradually wear those mountains down, carrying grains of rock toward rivers and oceans. Landscapes transform over millions of years, always moving from one state to the next. Volcanoes provide another glimpse of time's forward motion. Deep inside a planet, heat and pressure build until molten rock forces its way upward. When it erupts, lava spreads across the surface, cooling into new land. But that hardened rock never suddenly melts and leaps back into the volcano. Even planetary atmospheres follow this one-way unfolding. Over time, gases escape into space, chemical reactions reshape the air, and climates slowly transform. Mars once held rivers and lakes, but today its surface lies cold and dry. The story of a planet is written as a sequence of changes that never rewind. Gravity also plays its quiet role in this unfolding drama. Dust gathers into rocks, rocks into mountains, and sometimes entire moons form from scattered debris. Like an ice skater pulling their arms inward to spin faster, planetary systems evolve as matter shifts and reorganizes. But once those changes happen, the cosmic clock keeps moving forward. So planets themselves become living records of time's passage. Their craters, mountains, and atmospheres tell stories written over billions of years. Every layer of rock, every drifting cloud, marks another step in an irreversible process. And for scientists trying to understand these vast timelines, measuring time itself becomes one of the most powerful tools of exploration. For scientists trying to understand the universe, time isn't just an abstract idea. It's a tool, one of the most powerful tools ever developed. By measuring how systems change, researchers can trace the history of planets, stars, and even entire galaxies. The direction of time becomes a kind of cosmic clock. One of the clearest examples appears in radioactive decay. Certain atoms slowly transform into different elements as their nuclei release energy. This process happens at predictable rates, like a steady ticking hidden inside matter itself. By measuring these changes, scientists can determine the age of rocks, planets, and meteorites. The motion of planets offers another remarkable timekeeper. Worlds orbit their stars with incredible precision, tracing repeating paths across the sky. Like the steady rhythm of a spinning top or the swing of a pendulum, these motions allow astronomers to measure time across enormous distances. Spacecraft navigation depends on this cosmic choreography. Modern space missions rely on timing so precise that even tiny errors matter. Signals sent between Earth and distant probes travel at the speed of light, crossing millions or billions of kilometers. A difference of a fraction of a second can shift a spacecraft's position by hundreds of kilometers. So engineers track time with astonishing accuracy. Meanwhile, astronomers study stars themselves as markers of cosmic aging. Stars are born inside clouds of gas, shine by burning nuclear fuel, and slowly transform as that fuel runs out. By observing these stages, scientists can reconstruct the life stories of entire star systems. The universe reveals its history through change, Yet behind all these measurements lies a deeper question. Why does change always seem to move in one direction instead of the other? What invisible rule pushes systems towards certain outcomes and not their reverse? To uncover that secret, scientists turn to one of the most fundamental ideas in physics: entropy. To understand why time seems to move forward, scientists often point to a powerful idea hidden within the laws of physics. It comes from thermodynamics, the science that studies heat, energy, and how systems change over time. At the heart of this field lies a principle that quietly governs everything from melting ice to dying stars. This principle is known as the increase of entropy. Entropy can sound like an intimidating word, but its meaning becomes clearer with simple images. Imagine a neatly stacked tower of blocks sitting on a table. If someone knocks the table, the tower collapses into a scattered pile. Order easily becomes disorder, but the reverse almost never happens. The blocks don't suddenly jump up from the floor and rebuild themselves into a perfect tower. That outcome isn't impossible in theory, but it's unbelievably unlikely. Nature tends to move toward states that are more spread out and less organized. A similar thing happens when energy flows through a system. Heat naturally moves from warmer objects to cooler ones. A hot cup of coffee slowly cools down in a room, sharing its energy with the surrounding air. But the air never spontaneously gathers that energy to reheat the coffee. This gradual spreading of energy and matter is what scientists describe as increasing entropy. Over time, systems move from more ordered states toward more probable, more dispersed arrangements. Like ink diffusing through water or smoke spreading through the air, the process unfolds in one direction, and that direction quietly defines the arrow of time. So entropy acts like a compass for the universe, pointing toward the future. It doesn't push time forward like a force, but it reveals which direction change naturally prefers. From melting ice to aging stars, countless processes follow this same rule. And to see how this rule shaped our own cosmic neighborhood, the journey now turns to the birth of the solar system. About 4.6 billion years ago, long before Earth had oceans or mountains, our solar system began as a vast cloud drifting through space. This cloud contained gas, dust, and tiny particles left behind by earlier generations of stars. At first it was cold, diffuse, and quiet, stretching across trillions of kilometers. But gravity slowly began pulling this material inward. As the cloud collapsed, something remarkable happened. The spinning motion of the cloud gradually increased, much like an ice skater spinning faster when pulling their arms inward. Matter began to flatten into a rotating disk surrounding a growing young star at its center. That star would eventually become our sun. Within this swirling disk, countless particles started colliding and sticking together. Dust grains became pebbles, pebbles became rocks, and rocks slowly gathered into larger bodies. Over millions of years, these growing clumps formed the early planets. The solar system was assembling itself piece by piece. Yet throughout this process, energy was constantly spreading outward. As gravity pulled matter together, heat and radiation escaped into space. Order was forming locally, the sun and planets. But overall entropy in the system was increasing. The universe was still following its larger rule. Like a cosmic construction site, the early solar system was filled with collisions, eruptions, and intense radiation. Planets heated, cooled, solidified, and reshaped themselves over time. Every stage pushed the system further along its timeline. The arrow of time was quietly guiding the transformation. And from this long chain of irreversible changes, one small rocky world eventually developed oceans, continents, and an atmosphere. On that world, energy from the sun would begin driving new kinds of complexity. The arrow of time would soon shape something even more extraordinary. Because on Earth, the direction of time would become essential for life itself. On Earth, the arrow of time becomes far more than a physical principle. It becomes the invisible framework that allows life itself to exist. Every living organism depends on processes that move in one direction: growth, change, and transformation. Life unfolds as a story written across time. Consider something as familiar as a growing tree. A tiny seed absorbs sunlight, water, and nutrients from the soil. Over years, it stretches upward, forming branches, leaves, and rings within its trunk. Each ring quietly records another year that will never repeat. The same forward motion shapes every living creature. Cells divide, organisms grow, and bodies slowly age. Just like a candle burning its wax or a campfire turning wood into glowing embers, Life uses energy and releases heat into its surroundings. That constant energy flow pushes biological systems forward in time. This energy ultimately comes from the sun. Sunlight arrives on Earth as concentrated energy and spreads through ecosystems as plants capture it through photosynthesis. Animals eat plants, predators eat prey, and heat gradually radiates back into space. With each step, energy becomes more dispersed. Because of this steady energy flow, life maintains pockets of order within a universe trending toward disorder. Cells build complex structures. Ecosystems organize into intricate webs of interaction. Yet the broader environment absorbs the extra energy and entropy continues to rise. Life exists because of this delicate balance. So on Earth, the arrow of time shapes everything, from the formation of mountains to the beating of a human heart. It governs evolution, memory, and the passage of generations. But our planet is only one small chapter in a much larger cosmic narrative. To truly understand time's direction, we must now expand the view to entire galaxies. Now the view expands far beyond our planet, beyond even the solar system, into the vast architecture of galaxies. These enormous islands of stars drift through the universe, each containing hundreds of billions of suns. And just like everything closer to home, galaxies evolve over time. Their stories unfold across billions of years. Inside a galaxy, giant clouds of gas slowly collapse under gravity. From these clouds, new stars ignite like cosmic campfires scattered through the darkness. For millions or billions of years, those stars burn their nuclear fuel. Eventually, each one begins to change. Some stars swell into enormous red giants, growing hundreds of times larger than they once were. Others collapse under their own gravity, becoming dense stellar remnants. A few explode in brilliant supernovae, briefly shining brighter than entire galaxies. Each transformation marks another step along the universe's timeline. Over time, the galaxy itself changes shape. Stars orbit its center like countless runners on a cosmic track. Some drift outward, some fall inward, and others collide with neighboring systems. Galactic mergers reshape entire regions of space. Even black holes, those mysterious objects where gravity becomes overwhelming, play a role in this evolution. At the centers of many galaxies, supermassive black holes slowly grow as they consume surrounding matter. Jets of energy blast outward across thousands of light years. These dramatic events help regulate the birth of new stars. So across galaxies, the arrow of time continues its quiet influence. Stars are born, live their brilliant lives, and eventually fade into stellar remnants. Galaxies grow, interact, and gradually transform across cosmic ages. But to understand why this universal unfolding began at all, we must travel back to the very beginning of the cosmos itself. To understand why time seems to move forward everywhere, scientists look back to the earliest moment the universe can reveal. Nearly 13.8 billion years ago, the cosmos began expanding from an extremely hot and dense state. In that first instant, all matter and energy were compressed into a tiny, unimaginable volume. This event is known as the Big Bang Theory. At first glance, that beginning might seem chaotic. Temperatures were enormous, particles collided constantly, and space itself expanded rapidly. But in a surprising twist, the early universe was actually in a very special condition. It had extraordinarily low entropy. Imagine a brand new deck of cards still perfectly ordered in its box. Nothing has been shuffled yet. Nothing has been scattered across the table. In a similar way, the early cosmos started in a highly organized state. It contained enormous potential for change. As the universe expanded, gravity began shaping matter into new structures. Gas collected into clouds, clouds collapsed into stars, and stars gathered into galaxies. With each transformation, energy spread outward and entropy gradually increased. The cosmic deck was slowly being shuffled. This continuous increase in entropy created the large-scale direction we perceive as time. The universe moved from a simple beginning toward increasingly complex structures. Stars, planets, and eventually life all emerged along this unfolding path. Time's arrow may therefore be a direct consequence of the universe's unique starting conditions. So the mystery of time's direction may trace back to the birth of the cosmos itself. The universe began in an unusually ordered state and has been evolving ever since. Every melting ice cube, every aging star, Every memory we hold may ultimately reflect that ancient beginning, and that realization leads to an even deeper question about our place within this cosmic flow. 11. Topic. When someone pauses to think about it, the arrow of time shapes nearly every aspect of human experience. Memories accumulate behind us while possibilities stretch ahead into the unknown. History records what has already happened, while the future remains unwritten. Our entire sense of reality depends on this quiet, cosmic direction. Every photograph ever taken captures a moment that can never return. Every heartbeat moves life one step further along its path. Even civilizations follow this unfolding timeline, rising, transforming, and leaving traces behind. Time carries everything forward like a vast cosmic current, yet the same rule applies far beyond human life. Stars ignite, shine for millions of years, and slowly exhaust their fuel. Galaxies collide and reshape the architecture of the universe itself. Across billions of years, the cosmos continues evolving toward new states. In this immense timeline, humanity occupies only a tiny moment. And yet, in that brief moment, conscious beings have appeared who can question the nature of time itself. Creatures made of stardust are able to look back toward the beginning of the universe and wonder about the future still unfolding ahead. Perhaps that is one of the most extraordinary aspects of the arrow of time. It doesn't just move stars and galaxies, it carries awareness along with it. For a short while, the universe becomes capable of observing its own history and asking why the cosmic clock began ticking in the first place.